For the purpose of the signal processing, there must be a system, and the system operates on the signal, right? The system operates on the signal. For which purpose? In order to extract the information. And what is the objective of the signal processing? The objective of the signal processing is to get the better output, better information. So here the system will operate on the signal in order to get the better information, or in order to extract the information. So whatever is the information here, that is extracted information, is known as the output signal, right? This is also a form of the signal, as we have already described. What is signal? Signal is variation of any physical quantity or energy with respect to any one variable or more than one variable, right? So here we have to represent the signal in mathematical form, so that the algorithms, what is system? System will operate on the signal. Yes, it will operate on the signal. For which purpose? In order to extract the better information. So here better means noiseless. No? For example, say if there is any noisy signal, then if we are getting here the noiseless signal, we can say we are getting the better signal here, right? So here system itself is a rules and regulation, right? That is arrangement of the components or the arrangement of the some subsystems according to some rules and regulations. Now these rules and regulations may be known as the algorithms here, right? Means these algorithms will operate on this function, because we have described the signal in mathematical form. Now the signal, or we can say this is a function. This may be function of the time or function of any other variable here. So it will operate on this signal. Now for the purpose of the analysis, as we know, if this is the input signal and this is the output signal here, say ft, and say the system is represented by a mathematical representation as of the t here in continuous time domain, and output is said to be the yt here, that is also a function of the time, and here we are describing the input, output and system function in the continuous time domain here. Now the same can be described in the discrete time domain with the help of the, here this may be represented the fn or the xn, whatever is the suitable notation here, and then hn, and this is the yn. But generally we know, as we have described, that output is nothing but it can be calculated by the convolution of these two functions. That is the function itself, that is signal, is convolved with the system function, which describes the behavior or the nature of the system. Yes. So here we are getting the output of the system with the help of the convolution. Now what is the theme of the convolution which we have described? In this case we have described the input signal, either in discrete time domain or in the continuous time domain with the help of the impulses. Now what here the response of the individual impulse is calculated, then it is shifted and added, right? Shifting and adding procedure has been adopted here. Why? Because we have considered that this system is nothing but this is a LDI system, that is it follows the law of the linearity and time invariance. And linearity means what? The additivity that follows the law of the additivity and homogeneity simultaneously. Then we can say the system is linear. So it follows the law of the additivity and homogeneity, that is summation, and weighting the input signal here. And time invariance means here it is the response is not changing with respect, here the system's behavior is not changing with respect to the time, right? It is independent from the time here. That's why we will get here the output. If we represent the output in discrete time domain, then it is represented something like in this manner. If the Hn is the impulse response, then Xn minus k, and here not Hn, but this will be considered as the h of the k. Now we can consider the range of the k. For the causal system, this will be considered from 0 to some finite value, say m. That is the length, overall length of the m. That is 0 to m minus 1. Now if we see this expression here, then we will find that xn minus k. What is xn minus k? It is nothing, but we can say xn is multiplied by del n minus k. Right? And what is del n minus k? It will exist only when n is equal to k. Otherwise, it will be 0. Right? So we can say we are getting the response xn minus k is nothing, but this is the xn multiplied by del n minus k, means here the first xn will be represented with the help of the sequences, and then it will be shifted accordingly here. For the kth sequence, it will be shifted up to the length of the k towards the right hand side, that is delayed here, right? And after shifting, here the response will be obtained. Then whatever is the response, that will be added to the previous response here. We will get here the weighted shifted response of the input, right? Then whatever is the result, that will be added to the previous one. This is the concept of the convolution which we have described in the previous lecture. Now, what is the basis in order to know the response of the system? As we have described here, the system itself has to be described, means what are the rules and regulations which have to be applied on the input signal in order to get the output, number one. And the main important feature is that we have to describe the signal properly here, right? So, in order to describe the signal in a very proper way, now if we consider any real life example, say we describe the ear-brain system. If we consider here the ear-brain system, then suppose there is any voice, then the ear and brain system is not sensitive for the continuous changes of the oscillations. That is very fast, right? It is not sensitive for the very fast changes of the oscillations. As we know, here the voice signal or the speech signal moves according to the compression and rarefaction, and there is sudden changes of the oscillations, and the ear-brain system is not sensitive for these oscillations or this very fast rapid oscillation, but it is sensitive to which factors? It is sensitive to pitch, right? The number one is the pitch, that is related to the frequency here, right? And the second one is, say this is frequency here, and the second one is the amplitude of the voice signal or the speech signal here, the amplitude, and amplitude, or we can say the intensity here, intensity of the signal, right? And it is also sensitive to the duration of the signal. And the next one is the duration here. So, in order to analyze any signal, what are the requirements? Pitch, intensity and duration. Or we can say, if we represent any signal in the sinusoidal form, right? For example, say if the signal is represented something like in this manner, that is A sin omega naught t, right? Then it will describe all the features which are associated here. So, as we are here discussing, we are interested in order to analyze the signal and system, means how the signals will be processed. So, we have to represent the signal in very appropriate manner. And now, we will come to the point here, means how the signal will be represented in the frequency domain. Means, as we know, signal is a combination of the different frequencies component here. So, what is the impact of each and every frequency component? This will be analyzed here, and that will be known as the Fourier analysis, right? Now, in Fourier analysis, that is, if we consider here the signal, then as we know, the signal may be categorized in two categories. The first one is the periodic signal, and the second one is the which one? Non-periodic or the aperiodic, right? This is a periodic signal. As we have already described, what is periodic? It repeats itself after a certain duration, and aperiodic or the non-periodic. Now, if we consider any periodic signal, and as we have already described here, that signal may be categorized into two categories. One is the analog and another one is the digital or the discrete. And what is the beauty of the DSP? That discrete and digital signals both can be considered same during the time of the mathematical analysis. Whatever the rules and regulations are applicable for the discrete signal, the same are true with the digital signal also, right? So, here if we consider the periodic signal, then the energy associated with this one, say that Ft is the signal, then its square is considered, right, over the time, say from the T naught to say that T naught plus capital T, right, and dt. This is known as the energy. And if we consider the average of this one, that is 1 by P, if it is this total energy is divided by this duration, that is the capital T. And if we generalize this one for the total range here, that is up to infinite, that is limit T tends towards infinity, then it becomes power. And it can be described something like in this manner, that is definition of the power signal here, right? Now, any signal is said to be the power signal when its power is said to be finite and energy is infinite. So, if this is in the case of the periodic signal, it is a finite here, and periodic signals are known as which type of the signal? Power signal, right? So, this is a which type of the signal? It is a power signal. And we have already described this one, that is the what are the non-periodic? This is the energy signal, because in this case the power will become 0, but the energy will be finite. As we have described the power in this case, similarly we can describe the power associated with the discrete signal also. And in that case, what will be the power of the discrete signal? Here we will consider the x of the n, its square, right? Over the range, say here the n is suppose minus n to capital N. Now its average. What is the range here? Minus n to, yes, 2n plus 1. Very right. So this will be divided by 1 upon 2n plus 1. Now if limit, in order to cover the total range, here the limit n will tend towards infinity. And now this will become the power signal, average power signal. Generally these are written as the average power signal here, correct? Average power of the signal. So here if the signal is periodic, then how the signals will be represented in frequency domain? And if the signals are the energy signals, if the signals are said to be the periodic, that is power signal, means having the finite power but infinite energy, then these signals will be represented with the help of the Fourier series. Which type of the representation? Fourier series, right? And now we will discuss the concept of the Fourier series. What is the Fourier series here? Fourier series. And before the Fourier series, we come to the point of the vector here. Suppose we consider a three-dimensional plot, something like in this manner. Say these are the three-dimensional vectors. That is, one in this direction is v1. Here say this is the v2, and this is say the v3. These are the three-dimensional dimensions of the here. And suppose we consider a vector or a function f. Right? Now f will be represented with the, and this can be decomposed into these three directions here. That is, this is one component in v1 direction of the f, and it is the projection of the f in v2 direction, and this is for the v3. And we can write this one as something like in this manner, that now the f is written as, say, the c1 v1. Here say this vector is the c1 v1 plus this vector, and suppose this vector is c2 v2 plus this vector, say this is the c3 v3. Right? This is a general representation of any vector. If we consider the two-dimensional vector, then we can decompose it into the two dimensions. No? Here we have considered the three dimensions, so we have decomposed the vector into the three dimensions here. What is the meaning of this one? What is the basis of this one? We have considered the three directions which are orthogonal to each other. Or we can say the vector can be decomposed into the directions which are orthogonal to each other. In general, we can say any function, suppose we consider a function or the signal which are same, any function ft can be represented with the help of the functions provided these functions are orthogonal to each other. Now we consider a set of the functions. Suppose these functions are the phi1, phi2, phi3 and so on up to the phi n, which are orthogonal to each other. Then we can say this function ft can be represented over a time if the ft exists for this time, that is from t0 to t0 plus capital T, that is for the finite duration here. Then this function can be represented with the help of these functions, that is phi1, phi2, phi3 up to phi n. And what are the conditions here? These functions are orthogonal to each other. Now this ft may also be mathematically represented as, say, c1 is the coefficient associated with the phi1 plus c2 is the coefficient associated with the phi2 and so on up to the cn phi n, right? Or this can be written as ci phi I with a summation where the I is considered from 1 to n, right? So we have considered here the n functions which are orthogonal to each other, and hence we can represent the signal with these functions. Now if we see this representation here, then how many functions we have used here? N functions which are said to be orthogonal to each other. Now what is the possibility? Means how many functions or how many directions can be considered in space as orthogonal to each other? Only 3? How many? Infinite. Yes. We can consider infinite directions which are considered as orthogonal to each other. So what is the meaning of this one? It means in order to represent any function appropriately, that is without any error, how many functions are required? Infinite. And it is impractical, right? We cannot consider the infinite functions, right? Due to the limitations of the speed, and it will also require the undesirable memory space. So in order to convert this representation in practical domain, we have to consider the trade-off, that is approximation here. Now if we are approximating the representation of any signal, then what is the meaning of this one? It means we are not exactly representing the same function, but there will be some approximation error. Now this error may be positive or negative. So what must be our effort here? We will try to minimize the amount of the error, and we will consider here the square of the difference. Why we will consider the square of the difference? Yes, we can consider so that the negative can be also converted into the positive from here. So we will consider here the error. Say if we have represented any signal ft by this representation, that is Suppose we have considered the function ft with the approximation of the ft, that is approximated function I is said to be 1 to n and ci phi I here, then this will be the value of the error here, and its square. We will consider the square of the error here, and if we integrate this one over the time interval, suppose we have considered the time interval from t1 to t2 dt, this will be the total squared error here, right? Now in order to consider its mean, that is average value here, now this will be divided by the t2 minus t1, yes, that is t2 minus t1. Now this error will be known as the, which type of the error? We have considered the mean of the squared error, so this will be known as the mean square error, that is MSE. Now what is our objective? We have described here the mean square error due to the approximation, right? Now what is our objective? Our objective is to minimize this mean square error, right? So in order to, now the selection of the CIs will be according to this concept, that we will try to minimize the mean square error. Now if we are trying to minimize the mean square error, then this will be known as the minimum mean square error, MSE, that is minimum of the mean square error. Now in order to get the minimum mean square error, we will differentiate this one, and then we will find the here the maximum minimum, and then we will find the values of the CI. Now what will be the CI here? The CI will be calculated something like in this manner. If we apply this concept, that this mean square error will be minimized here, then it will be satisfied only when we will consider the CI as equal to this is t2 to t1, and say we have considered the two functions here, that is the phi m and phi n